Okay, well, I'd like to thank the organizers for inviting me. So today I've decided I'm actually just going to give a sort of try and give a sort of traditional talk idea in iPad. That's okay. I haven't started yet, so the title of my talk is going to be on tangent spaces and p-stable curves of Schubert varieties. And this is joint work with Victor Kreiman. And so let me begin with sort of the overall setup here. So as usual, we'll take G contained in B, contained in T. I don't want to belabor this too much. Say this is simple, and the Borel will contain the positive roots. And then I want to define Schubert varieties very quickly. And the main, well, I mean, of course, W is the Weil group. And X equals G mod B is the flag variety. And then as most people, or many people know, so the torus acts on X and the fixed points are of the form XB, where X is an element of the Weil group. And of course, technically, I have to take a representative for X and G, but I'll just use the same letter for X and for a representative. And then the only thing to keep straight is which kind of Schubert variety I'm taking. I'm going to take the B orbits or the B minus orbits. And in fact, I'm going to take the B minus orbits. So I'm going to use XW. Of course, it doesn't matter, but it just matters for our conventions. So XW is going to be the closure of B minus applied to WB, and that's the Schubert variety. And so the goal of this talk is to say something about the tangent space at the point X. So what I really mean is XB of XW, but I'm going to just write this as TX of XW. I'm just going to abuse notation, use X to denote both the fixed point and the Weil group element. Now, it's sort of surprising that although Schubert varieties have been studied intensively for many decades, really, this is the most, in a sense, the most basic question about a variety is what is its tangent space, and this is actually still not completely understood. But to start off, this is a representation of T, because it's a tangent space at a T fixed point, and so it's determined by its set of weights. Which I'll just call phi tangent, phi tan for tangent weights. Now X, of course, so X and W should be thought of as fixed throughout this talk. So of course, this phi tan depends on X and W, but I'm not going to put that in the notation. Now there's another geometric object which is related to this, which is much better understood. So let's let TE X of XW be the span of the tangent lines to T invariant curves in xw through x, really xb. And this is, so tx, so in other words, tex of xw is a subset, or it's a subspace of tx of xw. And just for the notational purposes, this, the set of weights here is we've denoted by phi tan. Here, the set of weights I'll call phi curve for curve. So that's at least you thought of as the curve weights, and the weights of your tangent to curves, subset of phi tan. And this, as we'll see, is very, the curve set of weights is very well understood, but the tangent set is not. So we do have this inclusion of the curve set of weights in the tangent set of weights, and we have equality in type A, but different in all other types. Yes. No, it doesn't depend on that, because it's no, because in fact the curves are all closures of U minus of orbits of root subgroups, and so the root subgroups are not going to depend on the isodic, basically. So it's basically sort of like a Unicode group. So in fact, this in fact is reminiscent of some stuff I did with Brian Bowe many years ago, because just to sort of state an example, there are many, so this is an example of how they can seem to be different. And I'm mentioning it partly for Brian's, partly I hope that Brian will be interested in the talk with people or remind him of this old paper. There are many examples of points xb in xw such that the cardinality of the curve weights is equal to the dimension of the variety. Actually, the cardinality of the weights is always, at least this cardinality is always, it's always true that always greater than they're equal to. But there's many examples, in fact, where this is equal to this, but xb is not a smooth point. Of xw, so the cardinality of the tangent set is strictly bigger than the dimension of xw. So in this paper with Brian, these would be the points where q is positive. Sorry, where q, these would be the set of smooth points where q is 0, sorry. So anyway, that's just an example. They can be very different. Now, the things I want to keep in mind for the remainder of the talk is that the curve set, or the curve roots, is relatively easy to describe. It also only depends on the Weil group. And the description is uniform across types. On the other hand, the tangent set is much more complicated. So it depends on the root system and not on the Weil group. So for types B and C, it will be different, even though the Weil groups are the same. It's been described for classical groups by Lakshmana and Seshadri but there's no, but it's complicated. And case by case. So there's not a known uniform description. Except in certain special cases. And to my knowledge, it's not known for exceptional types. So I mean, in a sense, So I think it's fair to say that even though it is known for the classical groups, it's not really understood in a sense. Like, really like a uniform description would be something that would just really help us understand what it is better, where it's coming from. And so before I tell you what the main result is, I want to give a preliminary definition. So the result of this talk does not answer the question of giving a uniform description of phi tangent. However, it's a general uniform result which gives some information about the tangent groups. And I think it's because it's uniform, it applies to the exceptional groups. And in some cases, it can be pushed further to give complete information for some parts of the wide varieties, like coding the school of wide varieties. But the definition is just if so let's let A be either Q or Z. Because I'm just going to use this because some of the basically for simply laced types everything is true with Z coefficients, but for non-simply laced types we have to go to Q coefficients. So the results with Z coefficients are will be stronger actually. But anyway, so if R is some subset of a vector space, or whatever field you like, let cone over A of R be the set of non-negative linear combinations of elements of R with coefficients in A. And so then the main theorem I want to talk about today is that the set of tangent weights is contained in the cone over A of the curve weights. And this is true in all types if A equals Q, and in simply laced types it's true if A equals Z as well. So that's the Z. Of course, the cone with Z is a smaller cone than the Q cone. So if it's true for Z, it's true for Q. So the Z statement is the strongest statement. So, and then just some equivalent versions of this. So one equivalent version would be to say that the tangent space and the curve space generate the same cone over A. Or another way of stating this is that the sets phi tangent and phi curve have the same set of indecomposable elements. So you can write everything in terms of everything. You can decompose everything into indecomposable elements. So have the same sets Okay. Well, one of the things I want to do is actually look at some of these cases more specifically using these conditions on the tangent space. However, there are many examples where there's not equality here, because I mean, you have to use the whole cone, because like in this work with Brian, we came up in all of these examples here that were produced up here, this example here with Brian, we have many concrete examples for elements in file groups where these two things in that example hold. In those examples, the tangent space and the curve space can all be calculated, and so one can look explicitly. And so one of the things we hope to do going forward is, look at these classical cases more carefully to see actually maybe we can get more insight into what's going on. So my answer is I don't know specifically, but looking at computer printouts from many years ago, there are many concrete examples where one can actually see that this is going to be an interesting thing to look at. I mean, I would expect that, well, maybe not, let me not say more, but I mean, the other thing that one can do is that in the classical cases, and I haven't done this, or we haven't done this yet, but one can look, so that you'll see in a second that the curve space only depends on the Gruha order, and that has actually a rather complicated description in terms of combinatorial terms for the exceptional, for types like B, C, and D. If you sort of do it in terms of sign permutations, it's actually a little bit complicated. It's not so bad, I guess. And then the tangent space condition is going to be a little different than the Gruha condition. And so what is I think, sort of another direction that we're hoping to look at is like, what exactly is the precise difference between these conditions? Like, and maybe that gives some more insight into what the difference between these sets is. So I think there are definitely, based on what's known, it should be possible to learn more about the relations in these cases. So, okay. So for most of the rest of the talk, maybe all the rest of the talk, I'm just going to discuss some of the ideas behind this, or ideas behind the proof. So the first reduction I want the Kazdan-Lustig variety, the KL variety. I guess in a leaf theory talk, when one sees K and L together, one probably doesn't have to write it out. The KL variety, I'm going to say Y of WX. It's XW intersect an opposite Schubert cell at X. In other words, more concretely, it's XW intersect with U applied to XQ. Now, near X, XW looks like Y of WX cross a vector space, which is just actually it's a representation of T. And this representation of T is easy to understand. So we can more or less forget about it because it's, representation is easy from the point of view of tangent spaces. And so it suffices to consider Y of XW. And so we have two subsets by tangent. If I just put the KL on top, I have tangent and curve spaces of KL, and then the main theorem follows from the stronger statement and it's funny because in this work with Brian many years ago, in fact, we, instead of looking at the entire set of curve spaces, we actually only looked at the curve spaces in the proofs of everything. We really looked at the curve spaces that lay in this Kazan-listic variety. So without even really thinking in exactly these terms, we found that this simplified the combinatorial picture quite a bit, because you don't have to deal with all these irrelevant set of groups, which might conceivably be rather large. Okay, so now the result relies on equivariant K theory and the zero-Hecke algebra. Now, I'm not going to say much about equivariant K theory, most likely. I don't think it will be time, but I will say. But let me tell you a little bit about, because I needed to sort of state what's happening. Let me tell you a little bit about the zero-Hecke algebra, which many of you will have seen before. I probably have mentioned it many times here. But anyway, so what is the zero-Hecke algebra? So T hat will be the character group of T, and R of T is the representation ring, which is the Z span of, or we could use a field if we wanted to, of e to the lambda, where lambda is in T hat, and it just multiplies by e to the lambda times e to the mu, is just e to the lambda. And then the zero-Hecke algebra it's the free RT module with basis H of U for U and W, and multiplication if I take S as a simple reflection, if I take a generator HS and I multiply it by HU, I get either HS of U if the length of S of U is bigger than the length of U, or I get HU if the length of SU. So I never go down, actually. I only go up or stay the same when I multiply elements together. So in other words, HS, if I square again HS squared, I get HS. And then the identity is just H1. So that's what the zero-Hecke algebra is. And the reason the zero-Hecke algebra enters is because it can be used to do computations in the equivariant K theory. So there's formulas for the pullback of a structure sheet of the Schubert variety to a point in equivariant K theory using this, which can be expressed in terms of the zero-Hecke algebra. So that's why the zero-Hecke algebra appears. Now, another thing I want to introduce is something called the de Mazur product, which I think I first saw this term in a paper of Alan Knudsen and Ezra Miller. So suppose that S is a sequence of simple reflections, not necessarily reduced. Then the de Mazur product I'll call it Z of S is defined by the equation. Suppose I multiply these elements together in the Hecke algebra. it's going to be h of something. But what that something is really depends on whether it's reduced or not. If I have repeated reflections, it's just going to stay the same. And so that the element that it turned that index it is called the de Mazur product. And so we have the in fact we have that z of s is bigger than or equal to the product of the reflections in S of L with equality if the product is reduced. Okay, so now for the remainder of this talk, I'm going to let S be a fixed reduced expression for X, for now the element X of it. So to back up for a second, the condition, I'm looking at the point XB or XB to be in the Schubert variety because that's the tangent space I'm interested in. That just means in this case that X is bigger than or equal to W in the Gruber order. That's a value condition. And so I want to fix a reduced expression once and for all. I'm going to let, just for simplicity, I'm going to let S underline I be the sequence I get by omitting the ith element. Now, I want to enumerate the inversion set, and it turns out it's not the inversion set of X that I want, but it's the inversion set of X inverse. That's because it's going to turn out that all these tangent spaces and everything lie in the inversion set of X inverse. So I'm going to let gamma 1 equal alpha 1. Gamma 2 will be S1 of alpha 2. Gamma 2 will be S1, S2 of alpha 3, and so on. And then the inversion set of X inverse is just the set gamma 1, gamma 2, gamma alpha. Now, for simplicity for the rest of this talk, I'm going to denote this by now. This is maybe a bad letter because it's often for simple reflections, but I'm going to let S denote this inversion set. So S is not the set of simple reflections, it's this inversion set. So, but it'll just save me a little bit of writing later on. Now, I want to define two maps from Z and X from S, this inversion set, to the violet group. I'm going to define Z of gamma I to be just the de Mazur product of what I get by deleting the ith reflection. And I'm going to write X of gamma I to be just the product here, S1, Si hat, SL. And for simplicity, I'm going to denote this element just by Zi. I'm going to call this element here Xi. Now, the map X does not. So maybe you may not like this. So this is maybe a little bit of awkward notation because I'm denoting X for this map and for this element here. So I trust that you will all be alert enough to keep track of the fact that when I'm talking about X the map versus X the element. So I don't know, maybe I could, if you like, I could try to pick a different letter. Let me not be too clever at this point. But the point is that the map X does not depend on the reduced expression because xi is actually just equal to s of gamma I times x. And yeah, so in other words, x of gamma I is just s of gamma I of x, and there's no reduced expression in that equation. But the map z does depend on the reduced expression. Z is the map z. If you just write down two reduced expressions, you can see that it's a different map. So the map z does depend on it. So the map z is a little bit. Anyway. So therefore, so I can define two subsets of S. I can define the set of S of z bigger than or equal to w. This is just going to be the set of gamma I, such that z of gamma I, which is really just zi, is bigger than or equal to w. Right? The set of elements whose so z and w, if you like, they can be thought of as, I don't know, in the paper we use the term weights. I mean, they're not torus weights, but they're kind of, it's like a weight. It's a map to a process of some kind of measure of something. So if you want to call it, anyway, it's a set of elements whose z map is bigger than w. And S of x bigger than equal to, S of x bigger than equal to w is a set of gamma I such that xi is bigger than equal to w. Now I should have said, maybe I'll just put it up here. Zi is bigger than or equal to xi. That's just what I said before. The De Mazur product is always at least as big as the ordinary product. And so Zi is bigger than or equal to xi. So that implies that the Z set contains the X set. Because if xi is bigger than w, then since Zi is bigger than xi, Zi is also bigger than w as well. So the S set, so the X set is contained in the Z set. Now, so now what Carroll and Peterson proved is that, in essence, they can state quite this way: the set of curve weights of the Casaubon-Lustig variety is equal to the S of x bigger than equal to w. So you see, that's actually rather nice, because all I need to do is now calculate some. I just have to look at some inequalities in the Grubauer order and see if they satisfy or not, and that tells me exactly what the curves that lie in this tangent space are. So it's completely uniform, and it only depends on knowledge of the Grubauer order. So we don't have as nice a result for the Z set, but what we have is the following. I'll just call it theorem A here for the moment, which says that the tangent space of the KL variety, the tangent weights, are contained in the cone over Z of the S of the Z set. So we don't have as much information. This is where cones come, but we don't have as much information. But we can prove the tangent space lies in the cone of the Z set. And so this is the part of the paper, or the part of these results. So this is where the only part really, but it's the important part, where the equivariant, where you have to use some kind of argument. Equivariant case here. So this is a non-trivial result, actually. And then, but in light of the Carroll-Peterson result and this theorem A, the main result follows. From, I'll call it theorem B, which says that in fact the cone over A of the Z set is equal to the cone over A of the S set, which is sort of more or less a purely root system kind of fact now. So, okay, so now, so let me just remark that in this case, again, in theorem B, the inclusion, this inclusion follows is immediate from what I just wrote down, because the Z set contains the X set. So therefore the cone of the Z set contains the cone of the X set. So this is immediate. And then to prove the other inclusion, we need to prove that the cone, the S of Z bigger than the W, is contained in the cone over A of S of X is bigger than the W. Then in that case, the cone, then we'll get the other inclusion of cones, and then we'll be done. If you take the cone of a cone, you don't change anything. The cone of the cone is the same. A is either Q or R. So A is just, so you can think most, A is Q, or I'm sorry, Q or Z. You can think of A as being Q, but the point is that in the simply laced cases, you can take A. Basically, the reason is that in simply laced cases, when you write roots as sums of other roots, you cannot have to use fractions as much. Okay. So let me just I think I will leave theorem A and probably not talk much about that today, but let me just discuss the proof of theorem B. So once we know theorem B, and then combine with theorem A, that is our main result. So let me just talk a little bit about the proof of theorem B. The discussion of the proof. Okay, so we want to introduce and relate various notions of indecomposability. So why, in a sense, you might say why indecomposability, but if you're talking about a cone, really the cone is spanned by its indecomposable elements. So we're going to try and basically look at these, prove some results about indecomposable elements. So the two notions I want to talk about are the notion of an increasing decomposition and an isodecomposition. And they're both a little peculiar in at first glance, maybe. But so a decomposition say alpha equals Ci of alpha I is called increasing if each Z of alpha I, Z is our function, each Z of alpha I is bigger than or equal to Z of alpha. Now, the reason we want increasing decompositions is we want to split things up into sums of smaller things in a sense. But we want the condition that Z bigger than equal to W be preserved by this kind of splitting up. In other words, if we started off with something whose Z is bigger than or equal to W, we want each summand to be bigger than or equal to W as well. If the decomposition is increasing, that's automatic because these alpha i's are always bigger than the original. So that's why we're introducing the notion of increasing decompositions to preserve the set where Z is bigger than or equal to W. And the second condition is this notion of an isodecomposition. So an isodecomposition is a decomposition of the form alpha equals C alpha 1 plus C alpha, same constant here, C alpha 1 plus C alpha 2, where alpha 1 and alpha 2 have the same, are roots of the same one. Now, it's a little bit mysterious why this would be a sort of interesting kind of decomposition. So I will explain in a moment or two why one might care about isodecompositions. Right? At the moment, it looks like a somewhat artificial condition, but it will turn out it's actually quite connected to expressions being reduced or non-reduced. So you'll see this in a moment. But then, so then the outline of the proof of theorem B is the following. So the first step is to say that every element, oh, by the way, so then I should say elements without such decompositions will be called increasing indecomposable or iso indecomposable. So there's kind of increasing indecomposable, it's kind of a weird sentence, but it means it doesn't have an increasing decomposition. So elements without these decompositions are increasing indecomposable or iso-decomposable. So the first step of the proof then is that every element of S, Z bigger than equal to W can be written as an increasing decomposition. So increasing decomposition in the sense I just said. Of increasing indecomposable elements. So that's sort of very plausible. You expect that when you take something, you decompose it. If it's not decomposed, if the two pieces are not indecomposable, you expect to decompose it again. You expect this process will eventually terminate and you get some decomposition like that. That's very plausible. The second term states that increasing indecomposable elements of S of Z bigger than equal to W are iso indecomposable. So, or equivalently, iso decomposable elements taking a contrapositive of S bigger than equal to W, Z bigger than equal to W have an increasing decomposition. And then the third step is that, and this is sort of where isodecomposability comes in, if gamma I is iso, so remember, all of our elements in this set S are of the form gamma 1, gamma 2, up to gamma L, right? So those are our elements of the set S. So if I have an iso indecomposable element of S of Z bigger than equal to W, then Zi is equal to Xi. So then the point is that putting these things together, I see I can get theorem B. So theorem B follows, because if I take some gamma in S of Z bigger than equal to W, I can write this as a sum of Ci of gamma of I. This is by 1, where Z of gamma I is bigger than Z of gamma, bigger than Z of gamma. So this is, so each of these gamma i's is bigger than equal to W. So I'm still in my set there. And then these elements here, so then by 3, gamma I is actually, so this here means that gamma I is in S of Z bigger than equal to W. But by 3, if you're an indecomposable element, Zi is equal to Xi. That means Xi is also bigger than equal to W. So by 3, Z gamma I is in S of X bigger than equal to W. And so then we decompose our element and turn it into S. So this is in the cone over A of S of X equal to W. So that's the outline of the proof. Now, so let me just make yet a couple more furthermore remarks on the various steps in the proof. So in this outline of the proof, the steps are a little bit more some are a little bit more non-trivial than you might think. So step 1 is actually a little bit not, it's not in a sense very deep because it's kind of doesn't really have much in the way of hypotheses. But it's a little bit subtle because you're using Q coefficients, and so it's not so obvious that the decomposition terminates. So 1 is a little subtle. With Q coefficients, a naive approach to decomposing may not terminate. So let me just give you kind of a model example. This is maybe not exactly this example. For example, but if we took, for example, this is kind of, just think of this as a model example rather than an actual example. We took S to be the set of positive roots in type V2. So we can write the short root epsilon 1 as a sum, as a rational combination of the two long roots, epsilon 1 plus epsilon 2 plus epsilon 1 minus epsilon 2. We decomposed it with rational coefficients. But now we can do the same thing to that first epsilon 1 here. It's 1/2 of 1/2 epsilon 1 plus epsilon 2 plus 1/2 epsilon 1 minus epsilon 2 plus epsilon 2 plus 1/2 of epsilon 1 minus epsilon 2. I just decomposed one of those epsilon 1s. Well, you can see I can do this again and again. I can keep decomposing these epsilon 1s in this way, and then this process will never terminate. I can constantly keep going on. So this, of course, is the wrong way to decompose, and in fact, the indecomposables here are just the simple roots epsilon 1 minus epsilon 2 and epsilon 2, and the correct decomposition is epsilon 1 equals epsilon 1 minus epsilon 2 plus epsilon 2. But I mean, if you're trying to prove it, how do you know you're not going down the wrong path? So there actually is something to prove. So, and then for item 2, for 2 steps, so for items 2 and 3, let me just explain a little bit how I said the indecomposable. So isodecomposability because you have the following are equivalent. So so the first thing is that the expression S1 of the SI hat, the SL is not reduced. So remember, reducing this holds that XI is equal to ZI. So that's very important, of course, in this proof. So let's look what happens when it's not reduced. And two, gamma I is isodecomposable in S of Z bigger than equal to W. So what this means precisely is that if it's indecomposable, what actually has to happen, you can say very precisely, in this case, once it, so let me just maybe I'll just sort of put this back. If it's indecomposable, there's sort of only one way it can decompose, in a sense. So what this means, you can show that if it's decomposable. So what I say decomposable means alpha I, well, C times, I'll just put the constant on C times alpha I equals gamma I is gamma J plus gamma K. Well, let's say J is less than K, right? I mean, they're not equal, so let's just say J is less than K here, right? So in this case, if this happens, then it's actually known already. Well, I went to prove. I think it's basically known. It's something close to it is known already. That in this case, in fact, J, I has to be sandwiched in between J and K. If you can write an element in the inversion set as a combination of two others, then that element has to be between the two other ones in the way when you enumerate them off gamma 1, gamma 2, up to gamma L. And this is just some kind of calculation with reduced expressions, kind of like what you would find in Humphreys' Coxeter group book, actually. So these kinds of these arguments here actually, can sort of be obtained by carefully reading the proofs of how you get the length function and stuff and reduced expressions in Humphreys' Coxeter group. So, but this, if it's isodecomposable, you have to have a situation where it's the sum of two roots which are sandwiched in between these two elements here, and so the point is that the reason and in this case, moreover, it's not so difficult to say that. First of all, you know that. I mean, maybe I'll tell you how you can obtain J and K very concretely. But in this case, one can choose. So this is one can choose J and K so that Z of J is bigger than equal to Z of I, and Z of K is bigger than equal to Z of I. So this is actually an increasing decomposition in our sense of like these increasing decompositions. And maybe just to sort of give you a sense of the flavor, how can one find this J and K? So one can find by taking K is the smallest index such that the length of S of 1 of the, the product S of 1 of the S of I, delete S of I of the S of K minus 1 is bigger than the length of S of 1 of the S I hat of the S of S. So what's happening is, of course, that because this expression S, when I delete SI, it's not reduced, at some point when I'm throwing on these reflections, the length has to drop. If we reduce, the length would keep going up. So when I go from K plus K minus 1 to K reflections, if that were a reduced expression, the length would keep going up. So because the expression is not reduced, at some point going from K minus 1 to K, the length has to drop. And so I choose K to be the smallest index such that this is true. And then J is the biggest index is the biggest index such that if I take the length, I do sort of the same thing again, S of j, S of I hat up to S of k is less than the length of S of j plus 1, S of I hat up to S of k. Kind of the same argument as before. The length has to be, they have to be, because these expressions are non-reduced, has to go down. And then in that case, if you pick this j and this k, then in fact you get these equations by some calculations with reduced expressions. This equation, can be shown to hold, and moreover, this can be shown to hold as well. So it's a kind of a distinct calculation with reduced expressions. So anyway, but it's sort of interesting because it connects this kind of decomposability in the root system with expressions, sub-expressions being either reduced or non-reduced, which is sort of interesting. So anyway, that I think is all I want to say at this point. So thank you for your attention.
So the zero.
That's right.
Okay. And this one appears in the
That's right.
okay. Can you maybe like sketch how you can use this to do computation again?
Well, where it comes in is the following. So we have say we have the inclusion of the point of the point xb into the flag variety x, which is just p mod b. So in the equivariant K theory of x, we have the class of the structure sheaf of the Schubert variety x of w. And if we can pull this back in equivariant K theory, and we get an element in the equivariant K theory of just the point xb, the equivariant K theory of a point is just the representation ring. And the theorem is, so I depends on x. It's really I of x, if you like. I'll put an x. I'll decorate this with a little x here. And so then the theorem is that I star, to take I star of x of O of xw, you're going to get the sum over all sub-expressions t of s. So t is a sub-expression of x, such that the product of the h i's, where I is in t, I hope I'm remembering this correctly, is equal to h of w. So here, remember, x is beginning to w. So there are going to be sub-expressions of this thing of the thing for x, which multiply to the thing for w. So let's get the sub-expressions. Now these things here all have, so the length of the number of elements in this, so the product of h of I multiplying to h of w doesn't mean that t has as many elements as the length of w. T might have more elements. So I'm going to define sort of the excess of this t to be the number of elements in the sequence t minus the length of w. Sort of the x, it's kind of measuring how non-reduced it is. And then what I have to take is I have to take the minus 1 to the e of t times the product over the elements I in t of 1 minus e to the, I can't remember whether it's plus or minus. I think it's, I just can't remember whether it's plus or minus. It probably depends on whether you're using positive or negative roots for the well. but let's just say it's let's just say it's I think it's actually minus here, but it might be a plus. But the point is that there's zero hectaalgebras entering into this pullback formula. And then once you know the formula, so the point is that this can be used to tell you that the t weights of the tangent cone of the functions on the tangent cone x of w at xd, and that the tangent cone, the functions on the tangent cone is a graded ring whose first graded piece is the dual of the tangent space. So this in turn gives you information about the weight, information about weights of t x of w. So that's where the equivalent comes into it. Yes.
So it's interesting to translate this into the language of Latin solutions.
Yes.
I'm wondering if there's interesting.
Well, it so happens that actually this weekend I gave a talk on this at this virtual AMS session. Alan Knudsen asked a very similar question. Actually, he asked if there was if you look at some kind of inverse images of these kinds of things in plot Samuelson resolution. So I don't know the answer to that, but it's worth it.
Let's make this very done.
Who's fucking next week?